The objective of this presentation is to discuss the various strategies that can be adopted to separate the isomers of hexane: normal hexane, 2-methylpentane, 3-methylpentane, 2,2-dimethylbutane, and 2,3-dimethylbutane. Let's have a look at the properties of the hexane isomers. Firstly, let's look at the research octane number. We see that the research octane number increases as we proceed from the linear normal hexane to the monobranched isomers and the di-branched isomers. The di-branched isomers have the highest octane numbers, and these di-branched isomers are the preferred components in high-octane gasoline. And therefore, there is a need to separate the mixtures of hexane isomers in order to recover components that have the higher octane number so that they could be incorporated into the gasoline pool. The boiling points of the hexane isomers are tabulated here. We see that the normal hexane molecule has the highest boiling point, and it is possible to separate the normal hexane from the branched isomers by distillation. And in industrial practice, this occurs in distillation columns that are termed dehexanizers. However, the separation of the di-branch for the monobranched isomers is more difficult because the boiling point differences are significantly lower. And the objective of this presentation is to consider separations of hexane isomers using adsorbents. The simplest approach that can be adopted to separate hexane isomers is to exploit the principle of molecular sieving. If we use an adsorbent such as LTA5A zeolite, LTA stands for Linde type A, and LTA5A zeolite contains 32 sodium cations per unit cell and 32 calcium cations per unit cell. The LTA structure consists of cages separated by windows that have dimensions of about 4 angstrom to about 4.6 angstrom. It is possible for a linear molecule such as hexane to diffuse easily or relatively easily through the 8-ring windows of LTA4A zeolite, whereas the monobranched isomer and the di-branched isomers are limited in their ability to hop from one cage to the adjacent cage because the dimensions of the molecules prevent the intercage hopping. And therefore, in principle, it is possible to separate the normal hexane from the branched isomers using LTA5A zeolite. The processing scheme currently used in industrial practice is shown on this slide. Consists of a feed mixture that is isomerized in a reactor with modernite catalyst to produce a product containing the isomers of hexane, and this mixture is sent to an adsorption unit containing 5A adsorbent that allows selective uptake only of the normal hexane isomer because of configurational considerations. The mono and the di-branched isomers are prevented from entering inside the pores of 5A zeolite. The rejected components consisting of monobranched and di-branched isomers can be incorporated into the gasoline pool, and the normal hexane can be recycled back to the isomerization reactor. The preferred processing scheme, however, is to select an adsorbent that separates the linear and the monobranched isomers from the di-branched isomers, so that the di-branched isomers with the higher research octane number can be incorporated into the gasoline pool, and the linear and the monobranched isomers can be recycled back to the isomerization reactor. The question is, which adsorbent should be used to effect this separation of the mono-branched and the linear from the di-branched? One candidate adsorbent that is capable of separating the linear and branched isomers from the di-branched isomers of hexane is Fe2 BDP3, that has triangular channels of 4.9 angstrom size. The details of this metal organic framework are provided in this article. The isosteric heats of adsorption of the hexane isomers in the 4.9 angstrom triangular channels of Fe2 BDP3 are shown in this graph here. The hierarchy of binding strengths is normal hexane, 2-methylpentane, 3-methylpentane, and the di-branched isomers 2,2-dimethylbutane and 2,3-dimethylbutane. The linear hexane molecule can align itself along the vertices of the triangular channels, which each of the carbon atoms effectively interacting with the channel walls. The van der Waals interaction of the more compact monobranched and di-branched isomers are lower in strength than that of the linear isomer. Breakthrough experiments show that the hierarchy of breakthroughs follows the hierarchy of binding strengths. The di-branched isomers are the first components to break through, followed by 3-methylpentane and 2-methylpentane, and finally the linear hexane molecule breaks through the fixed bed adsorber. Therefore, Fe2BDP3 can be used as adsorbent in a PSA scheme shown in the previous slide, wherein the first two components that are rejected into the gas phase can be removed and incorporated into the gasoline pool, and the adsorbed components can be desorbed and recycled back to the isomerization reactor. Let's consider the traffic of linear hexane and monobranched isomers 2-methylpentane and 3-methylpentane as it moves within the triangular channels of Fe2BDP3. The mobility of the linear hexane molecule is higher than the mobility of the monobranched isomers, because the monobranched isomers are more strongly confined within the 4.9 angstrom channels, whereas the linear isomer is less strongly confined. A special feature of hexane separation with this morph is that adsorption and diffusion proceed hand in hand, because hexane, which has the highest adsorption strength, also has the highest diffusivity value, and this combination of adsorption and diffusion being synergistic is useful in fixed bed separations. The di-branched isomers 2,2-dimethylbutane and 2,3-dimethylbutane have compact configurations and are very strongly confined within the triangular channels. Their diffusivities are even lower than those of the monobranched isomers. The combination of poor adsorption strengths and low diffusivity values makes for earlier breakthroughs in fixed bed adsorbers, and this is desirable from a process standpoint, making Fe2BDP3 a viable candidate for commercial use.